My microphone is dominating my field. Okay, let's see how.
All microphone all the time.
Yeah. Let's see if I can do this a little bit differently. So I'm one washer short. So I'm like,
is that like
totally
like you're crazy? You're one washer short of a stable microphone?
Yes, that is exactly what is occurring. I'm one washer. No, I don't know how. Bah! Okay. I hate everything.
We're live, by the way. Are you done?
No.
I'll just wait.
Okay, now I'm done.
Ooh, that sounds really
Very
good.
simple fact that it can go no further.
That sounds really good, though.
Okay.
Yeah. Don't worry about it.
With this.
Yeah. So I think you've made everything better by dismantling in rage your setup.
Sometimes you have to rage microphone.
What's happening?
Like you, I am now happy to say we will be meeting in Joshua Tree in June. That trip is fully ready to go. Beyond that, I'm getting ready to we're continuing to work on CosmoQuest, and we're getting ready to do awesome things with the OSIRIS-REx mission, and that's all I can say, which is so frustrating.
Too much science, if that's even possible.
It's fabulous.
I'm going to say hi to some people. Hi to Eris Echevarria, Bill Sugden, Chai Latte Nebula, Chris Bamford, Coalfire, Dusty Reichwin, Enoch, Eric Schneider, Esther Gagne, Gordon Dewis, Guido Bibra, Harry M., Henry Bo Anderson, James Aberson, Janelle Duncan, John Seffield, Johnny J., Larry Beckham, Leonard Clark, Nancy Graziano, Nichols of the Yard, Paul Gracie, Rich 901, Tak Tang, Tom Van Scotter, Yamagashi-san, and Zapfen. Hey, everybody. Welcome to this part 3 of our ongoing series. I think I can stick around to the end. I've got to go pick up my daughter from a ferry in
so I know what you meant, but what my brain heard was Fairy, and I imagined Tinkerbell floating around with your daughter.
You know what they say, right? Always be yourself unless you can be a fairy, and then always be a fairy.
I think the phrase is Batman.
Batman, right. Not a fairy. Batman.
No, always be yourself unless you can be Batman, in which case be Batman.
Yeah. Man, what's happening over here? Nothing. Beautiful weather, bordering on drought.
Oh, no.
Yeah. Hi, Peter Wolsk.
I so wish I could send you water because the Mississippi is like feet and feet above flood level.
I know. But we hooked up our irrigation system, so now we're getting the watering going. Hey, Rich Wilson, Kevin N. People are like, what about me? Oscar Arenas, Tad Awesome, Citizen Case, Steve Chisnell. There you go.
So one thing I have been up to that I'll be promoting is this necklace that I'm wearing is one of the ones I made.
Right on. Closer to, can you dismantle it and hold it closer to the camera?
Yep.
John Moschita. I don't know who that is. Monchita? Too close.
Doesn't want to focus. No, it's that it's focusing in the wrong place.
Oh, there you go. Oh, that's fantastic. So it's like a teeny tiny little version of your little planet?
Yep, and it's under glass and fully wearable. And there are a bunch of them up on Etsy. And our store is 739 Studios because that is a prime odd number. And somehow that just seemed to fit everything. And I'd really be happy if they sold.
Well, I think that would be great. Okay, cool. Well, so if you're wondering what it is that you stumbled into, we're going to be doing a live episode of Astronomy Cast. We are going to spend about 25 to 30 minutes talking about how to figure out how old things are. Is this the end of the series? Should I mentally reach the cosmic microwave background radiation as I go? I'm feeling like star. We covered stars pretty heavily last episode, so we'll probably do a quick synopsis on that. Talk about globular clusters, ages of galaxies.
So
pulsars.
We have non-radioisotope versions of aging stars.
Yeah.
So I think 20 minutes on or 15 minutes on finishing up stars and 15 minutes on the rest of the universe,
Yeah.
and we're good.
Ages of Galaxies, and then the Cosmic Wiki background.
Yeah.
Okay.
Yeah.
People say you've got a bit of a challenge when you take your earbuds out now. They're wrapped. Now they go
Yeah,
under your
I'm
neck.
fully aware that I did that,
Yeah.
and I was just too lazy to care, and I am aware of the problem I have set up for myself. I will fix it so it stops bothering people.
People are saying that I'm learning to say the names very quickly. That's because I see the same names week after week, which is awesome. So I'm getting to remember and come up with ways to pronounce everybody's names, even the fine points, like Guido Bibra, as opposed to Guido, which is just would be my instinct. So,
Okay.
yeah, is that not yours?
No.
No. Wow. Okay, and then we'll stick around and answer your questions about space and astronomy, and I may have to leave early. We'll find out what happens.
Okay.
All right.
And I promise to compensate on the mispronouncing of everyone else's names. I just know how to do Guidos.
Oh, there you go. All right.
I am ready to record.
Let me just
Are you ready to
I am ready to record. Yes.
Okay, I'm simply making sure that we don't have an echo. Hold on. That was a mistake that I made last week. And the dog in the
Yeah.
background. Dear God, that dog.
Is that your dog?
It is. It's my puppy who has decided that there are many things in this universe that she hates, most of which are called squirrels and trees. And she does the thing I've never had a dog actually do, putting her paws on the tree and barking up the tree.
Yeah, one of the advantages that we have of having a deaf dog, she just does not catch any of that stuff going on. If she can't see it, it doesn't happen.
Do I need to go bring my dog inside?
I'm gonna say yes. If this
Yeah,
is if this
I will
is
be
what
right back.
if this is what the show is going to be like, then yes.
Yeah, I will return.
All right. RWBY. Is that a Rooster Teeth thing? Is there another? Ruby? Wesley is noting that Costa Rica's weather was better than back here in Iowa. Exactly. So much nicer. Actually, it was like freezing cold when I got back home, and now the weather has gotten just beautiful, but droughty. So it should be pouring rain here. I have not seen Ruby. Is Rooster Teeth still a thing? Did they go out of business? Did they get gathered up by something and then sold off to Disney or something? Did you... I don't know if people have heard... We were talking about this. Oh, this is how this is going to play out? You're going to have a dog and you're... Hold a dog like a baby while you... Two dogs like babies while you do the show and get kicked in the face?
No, I'm going to put her down in just a moment. Just wanted to make sure she got in the house.
Susie says it's easier to edit without the barking.
Okay. Seriously? Go away. Go.
Are you done? Are you ready?
Yes. Yes.
You sure?
Mm-hmm.
Okay. All right. Say when you're ready.
I have pressed record, and it is recording.
I have also pressed record, and it is also recording. Here we go. Astronomy Cast, episode 524, Age and Origins, part 3, Beyond the Solar System. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing great. I have, literally no news.
That says something, considering you're the publisher of Universe Today.
Okay, possibly we have some news there. And if you want to find out what that news is, you should sign up for my weekly email newsletter at universetoday.com/newsletter, which I just sent out the door. Maybe that's part of it, is that whenever I write my new newsletter each week, it just completely empties out of my brain. Oh, Sky and Telescope is for sale, so somebody should buy that and take good care of it, because
it's true, please.
Yeah, because Sky and Telescope was like the most meaningful piece of magazine periodical growing up. I found a pile of Sky and Telescope magazines at a garage sale on Hornby Island, and I must have gotten my hands on like 40 or 50 of them. And so then,
wow.
Yeah, so it was this huge collection that covered like a decade. And someone was obviously a collector. And so I just went through them, and that's what taught me to be interested, or that's what taught me the fine details of astronomy, what objects were up, how to find them, techniques, and things like that. And so I know for a lot of people that are listening to the show, Sky and Telescope was the Bible for astronomy, like really good, hard science, as you know, observing guide, and it's too bad that it's sort of gone through some tough times. People keep saying, "Will Universe Today put it in offer?" No, I don't think I can afford it. I wouldn't even know what to do with it. We don't kill trees at Universe Today. We just push electrons around. So, but if someone does have money and wants to take care of it, it should be up for sale in the next couple of months. All right.
Okay. On that cheerful note,
we learned how to figure out the ages of objects in the solar system. Now we push out into the deeper universe. What about stars, galaxies, and even the universe itself? How old is it all? All right. So we kind of half taught people how to figure out how old stars are, but we have not taught people how to figure out how old stars that aren't the sun are very well.
That is fair. That is fair.
So let's start there with how do we figure out how old stars are in the wider universe?
Well, there are a bunch of different ways. And the newest way that scientists have come up with is to actually look at how fast stars are rotating. And this was something that I never knew would be a thing. And one of the factors I loved most was the press release actually said how to pronounce this technique, which is gyrochronology.
I love that term.
It just like gyroscope. The idea is that stars change their speed over time as they undergo mass loss, and as that mass is carried away, so too is the angular momentum of the system. And so it's super difficult to measure the rotational velocities of stars, but if you can do it, this is the cool new way that the cool kids with the best instruments are measuring the velocities of stars and their ages.
So I'm trying to think about how you would measure that, right? How do you measure the rotation of a star? And then how do you know what the rotation tells you about the age of the star? So how do you measure the rotation of a star first?
The most accurate way to do it is to look at stars that have sunspots and measure how long it takes for that sunspot to go across the face of the star. So just like we measure the rotation rate of our sun to first order by watching those little sunspots march across the front, we can look at changes in brightness of distant stars that are tied to changes in whether or not we're seeing sunspots on that distant star.
That's amazing.
Yes.
Right? That you can see sunspots moving across the face of a star, but I guess by like how much light they're putting out, and then you can use that as a way to say, okay, that's probably a sunspot, and then when it returns to that same level of brightness, just a couple of say weeks later, then that's probably that same group of sunspots is moving across the surface again. Mind bending.
Yes.
Now, I would also assume that there's some way, sort of, with the Doppler effect that you can measure the sides of stars to sort of get a sense of how quickly they're turning. One
It's
part of the star is
well,
moving away from
if
you, and one part of the star is moving towards you.
if only you could separately measure the light coming from either side of the star, but we don't quite have the capacity
Okay.
to do that. So what we do instead is we look at the line broadening, but there's a complexity to this that can add a lot of error to the measurements, and that complexity is gravity. So the surface gravity of a star also affects the thickness of the spectral lines of a star. So if you can accurately figure out what kind of a star it is, what kind of mass it likely has, you can make assumptions about what its surface gravity will be and make assumptions about how that gravity will affect the width of the lines. And then you can assume that whatever is left behind is line thickening due to rotation. But it's a much less precise
Right.
method, although to be fair, we're looking at sunspots on distant stars where we're going, aha, its brightness dipped this many percentages and then came back up in a non-periodic way. Therefore, this is a sunspot. So this is one of those techniques that is sort of like, wow, there's a lot of error, but this is cool.
That's amazing. Okay, so that's your method for stars. So now we are measuring the speed that a star is turning. How do we then use that to figure out how old the star is?
Well, this is where you have to couple different methods. And just like we have a distance ladder for measuring the distances of stars, we kind of have an age ladder for measuring the ages of stars. And this age ladder is based on our understandings of stellar evolution that is then grounded in radioisotopes. And then we extend it out now with the rotations of stars. So the science teams that did this, they were looking primarily at main sequence stars. These are stars like our sun that are burning primarily hydrogen and helium in their core. And they were looking at late F, G, K, and M stars. So these are the smaller kinds of stars. And in systems where you have a main sequence, where you have stars that are still in the process of evolving, this means that you may have your biggest stars have already, well, stopped being main sequence stars. They've already evolved away. And because stars predictably from largest to smallest evolve off the main sequence, finish burning that hydrogen and helium in their core, other processes for bigger stars, as they evolve off, that point says, okay, everything more massive than this is done burning. Everything below this is still burning. And from radioisotopes, which we talked about before, we can get precise ages for that point for stars that are close enough to get high enough resolution spectroscopy. And we use stellar evolution models for systems that are further away that we can't accurately measure. So through a combination of stellar evolution models and actually getting to measure things from radioisotopes, we can say, okay, when we see this turn off, it means this age. When we see this turn off, it means this age.
Now that technique of measuring the spins of things can tell you, like how some degenerate objects are, how old they are. And I think the best example of this, right, is pulsars, all neutron stars, that
And
whole process, right? By measuring the spin rate, you can tell kind of how old the object is.
And this is also reliant on them being in isolated systems. If you have a massive star that goes supernova, collapses down to something tiny, it's initially going to have a much larger rotation rate. Over time, its rotation is going to slow for a whole variety of different reasons. but this starts to give you relative ages of different systems. Now, the reason I say that this only works with isolated stars is it's possible to transfer angular momentum between stars in a binary system. So anytime you're looking at the rotation rate of something, it needs to be the non-influenced rotation rate. We can see this in our own Earth, where we're, to some estimations, a binary planet with our own moon. And our rotation rate is slowing as the moon moves further away. And it's this tidal locking of our two systems that is in the process of heading towards being completely tidal locked, that we're changing the rotation rates of both worlds as we evolve their separation.
Right. I mean, like, when a star goes supernova, it, if it's more massive than, much, whatever, 5 times more massive than the sun, then you get a neutron star as the outcome. And they start out having a ton of that that angular momentum. They're spinning very quickly. This is a pulsar, and the fastest millisecond pulsars are the ones that are the freshest, right? And then as over time they are losing their energy. How? Right? What is causing them to slow down?
So you can actually end up with the stars deforming themselves, filling their Roche lobes, essentially, where the side of each star that's pointed towards the other deforms and gravity tugs extra on that. And so you have this slowing because the stars aren't perfect spheres because they're pulling on each other. So this is a tidal effect. You also have mass loss effects, mass transfer effects, which can speed up one star while slowing down the other.
Well, I'm talking more like an individual star, not necessarily one that's in a binary system, right? Like, how does an individual star
mass
slow
loss,
its rotation, but also
expansion,
and gravitational waves, right? Like, can't they, or not gravitational waves, but can't they lose momentum? Just like into space itself. I forget the method. Maybe maybe it's only in a binary system.
You can have gravitational radiation, and that is something that we worry about with compact stars, with compact star binaries.
Right.
For your average binary system, that is less of a concern, and it's more like you shed mass, you slow down. Unlike humans who shed mass and speed up, but stars have their own way of working.
So what about white dwarfs?
Now white dwarfs, they are awesome insofar as they start out super hot. It's a leftover stellar core from a star like our sun that has poofed off its outer atmosphere to form a planetary nebula. And that diamond in the sphere that is left behind is white hot initially, but it's not generating new heat over time. It's simply radiating a heat away to outer space. And this means that over time, it is cooling off. It's becoming less luminous. And it should be doing this in a way that is completely predictable. The question is, are our theories correct? And this is the modern challenge, not whether or not this technique can be used, but how well do our theories match reality? Because there's phase transitions that go on as the star cools. That new thinking is that these phase transitions within the star may cause them to linger at one particular apparent luminosity for longer than they might remain at other apparent luminosities.
But over time, give it billions of years, trillions of years, they should cool down to the background temperature of the universe. And so you should be
black stars.
Yeah, and so you should be able to measure the temperature of a white dwarf and know roughly how old it is, knowing what temperature it probably started at.
And this is where reading really old astronomy papers and literature becomes fun, is you have astronomers that were talking about black dwarfs, black stars, and they're simply talking about really cold stars, not some euphemism for black holes.
Right.
So that white dwarf over the fullness of time is going to become invisible to the human eyeball.
That's really cool. All right, so we have a way of trying to figure out how old a lot of stars are. If they're in binary systems, then that messes things up. What about galaxies themselves? Can we get a sense of how old the galaxy is and when it came together?
We can get a limit on it. So if you look at a star system that doesn't have ongoing star formation going on, and you measure what are the general population of the stars, red and dead is the phrase that's generally used, that tells you that that galaxy is at least old enough to have formed and evolved all those stars. So it puts a limit. And then the other thing is we're looking back in time with most galaxies. So when I look at the light of a galaxy that has been traveling to reach me for 12 billion years, because light doesn't move instantaneously. So the further away something is, the further and back in time I get to look. When I look at these 12 billion light year away systems, and I see stars that are millions to maybe even billions of years old. Well, not billions at that point, millions to hundreds of millions of years old. That tells me that system must have formed at least, if there's 500 million year old stars, and I'm looking at something 12 billion light years away, that means it has to have formed at least 12.5 billion years ago. And it's these limits that are really exciting to us as we look back at the furthest systems, because we get to see galaxies that we know are in the process of forming because they haven't been there long enough for this to be their fourth generation of dying stars. If I look at a nearby galaxy and it's all red stars, it might have gone through 7 generations of star formation and have formed at the beginning of the universe. So looking at galaxies, I have to combine the redshift information that tells me loosely how far away it is, supernova information if I've got that, and then combine it with how old are the oldest stars that I'm able to tell are there by the combined spectra of light from that system.
There's actually a couple of other objects that I just realized that are connected to that. One is to know how old globular clusters are.
Yes.
Because they're often used as a way to age
our own system.
Our own galaxy, right? So when we think of these globular clusters, these gigantic balls of hundreds of thousands of stars, how do we know how old they are?
It goes back to that main sequence turnoff that I spoke about earlier in the show. Globular clusters are these fabulous things that we don't fully understand the formation mechanism for, where all the stars in the system are made out of one kind of material, one mixture of stardust and gas, and all the stars were formed out of one epoch of star formation. And since they're all made of the same stuff, they're all going to evolve in similar ways. Since they were all formed at the exact same time, that tells me that the largest stars I see on the main sequence are indicative of the age of that solar system, the age of that globular cluster. So if there are stars on the main sequence that would die in, say it's an open cluster instead of a globular cluster, that would die in 500 million years, if those stars are still on the main sequence, that means it's less than 500 million years.
Right.
Now, if I look a bit bigger and I'm like, oh, there's nothing there that would live for 200 million years, all those things have gone supernova, that starts to give me this narrow window of how old that system is. Now I can keep doing that, keep going further and further down the main sequence until I get to stars that are billions of years old. Now the complexity here is these are theoretical ages based on how long do we think it takes to go through all these different stages of evolution. And again, when we can, it's great to be able to get high resolution spectroscopy and start to nail down these ages, not just with the main sequence turnoff period, but also by looking at the compositions with high resolution spectrographs and measuring through nuclear cosmochromography what is the age due to radioisotopes.
Right. I mean, I love this idea that you look at a globular cluster and you don't see any stars that can live for 10 billion years.
Yeah.
Therefore, or that all of the 10 billion year old stars have died. Therefore, the globular cluster is older than 10 billion years. Which is just, and then you can just say, oh, but there are some 12 billion stars that can live 12 billion years. Therefore, it's possible that cluster is less than 12 billion years old, which is an amazing idea. One more sort of astronomical thing, and then I want to move to sort of the big question. So we see, and we report on this all the time on Universe Today, like we see a supernova remnant.
Yeah.
And we'll say, oh, this supernova remnant happened 5,000 years ago. How do we know that?
That comes down to there isn't anything to stop a bullet in space. And when that bullet is part of the outer layer of a star, it just keeps expanding out at a fairly constant rate. With some supernova remnants like the Crab Nebula, we can look out and over decades, we can actually see in the images, and this goes back to talking about Sky and Telescope at the beginning of this episode. Sky and Telescope had a fabulous collection of these images that they used to distribute to schools, where you can measure with a ruler on the images how the outer layers of the nebula are moving outwards relative to the stars. And by knowing the dates that these different images were taken and the distance to the system, you could measure the expansion rate. Right. Now, if you know the expansion rate, you work it backwards to when was this thing compressed down to the size of a star, and that gives you the how long has it been expanding. Now, we are lucky with some of these supernova that we actually have archaeological records, so we can check our work. And it's amazing to be able to look out and say, yes, that particular supernova was observed by Kepler, by Brahe, by the Chinese, by these indigenous people, by Hecht Space Telescope in 1987. And see the remnants expanding over time, and then be able to look at other things where we see these light echoes traveling through space, and then we can track them back and say, there was a supernova here, and even though no one noticed it, we know when it happened.
All right, so we've got enough time to ask the big question, which is, how do we know how old the universe itself is?
It actually builds on how we know how old supernova remnants are. We look at the expansion rate of our universe, and we run it backwards. Now, there are checks and balances. There are other ways that we're like, does all of this make sense? We look at the fine detailed structure in the cosmic microwave background, and that helps us understand, expletive, the cosmic microwave background had to have gone through a massive inflationary period. Therefore, from this massive inflationary period, it was a non-smooth expansion. But we can work things out to get at detailed theories that replicate what we see, to model the first 300 to 400,000 years of the universe, to replicate the observed cosmic microwave background. From there, we can measure the expansion rates as a function of time and see the gradual changes that are taking place. And then we just do an integration. It's all calculus all the way down.
I did some research in this on an article one time, or video, and like, if you could see the cosmic microwave background, this is this moment when the universe became transparent and light was able to escape out into the universe for the first time, and if you could be there to see it when it happened, you would see like a reddish glow.
Yes,
would be the color that you would see. But now we see it as the cosmic microwave background. And so it's that redshift that's happened over time as those regions that were once red have now been pushed away that we see them, that the wavelengths have been stretched out to the point that we see them in microwave. And that's your math, right? That tells you what age of how much expansion time would it require to take what was reddish light in the beginning to make it look like it was microwave light today.
And that gives you a limit. So we know how fast the cosmic microwave background is moving away from us. Now, the question is, has the rate that the universe is expanding changed? And it's sort of like, if you know that I was going 90 miles per hour for the first hour of a journey, and you know that I'm going somewhere between 70 and 100 at the end of the journey, you can guesstimate, based on knowing the distance, how long it took me to travel, if you just assume I went 90 the whole time. But if my speed varied at a constant rate, which is what we think now happened, is the acceleration, there was an acceleration term to the expansion. It gives you a finer detail. This is where we keep adjusting our numbers over time.
And I mean, we look at, say, I think when we started Astronomy Cast, the estimate was 13.5 billion years old. Then it went to 13.7 billion years old. And now we're at 13.77, I think, billion years old. And the error bars are getting narrower and narrower at this point. Are you looking at the exact most recent estimate?
Yeah, because in my head, it's 13.772 according.
There you go.
Those.
Yeah.
Planck measured at 13.82.
Oh, there you go. So Planck is the newest measurement. The most accurate measurement of the cosmic microwave background gave us this incredibly accurate estimate. Why? Why does a more accurate measurement of the cosmic microwave background give us a more accurate understanding of how old the universe is?
This is where it starts to come down to matching the fine-grained structure in the background, which starts to tell us how long it was before the Big Bang. So when I was in grad school, I remember learning it was 300 years from zero to cosmic microwave background. We now tend to teach it's more like 400. So that gets you part of the difference. And then it's
1,000.
Just a more... Yeah, it's now
I think it's 380,000, or I forget the exact number. Yeah, but yes,
it's now a also more accurate color measurement. So when you combine the more accurate color, the more accurate understanding of how long it took, and it also gives us a more accurate understanding of the geometry of the universe, because how you expand and how the geometry is, it all factors together. So there's multiple different things at play. There isn't a simple answer, but it all comes down to knowing how long it took to get from zero to cosmic microwave background, how long it took to get from cosmic microwave background to now, based on changing expansion rates.
Amazing. So there you go. That's how you know how old everything is, if anyone asks. Pamela, do you have some names to read this week?
I do. So this is the part of the show where we're working our way through thanking the wonderful patrons that, well, help us pay Susie. Without you, Susie would not be paid. So thank you, thank you, thank you. This week we want to thank someone with a complicated name. Kenslia Pantnienko.
Nice.
Shannon Humber, David Gates, Eric Frenger, Rachel Fry, Frederick Shorgy, Claudia Mastrani, Tyrone Fong, Neuter Dude, Darcia Daniels, Kristen Brooks, Thomas Tubman, Jimmy Berkson, Arthur Laz Hall, Omar Del Riviero, Chad Colopy, Mark Stephen Raznak, G4 184, and William Lauer. Thank you for being part of our Patreon crew. To those of you who have not yet said Astronomy Cast is worth $5 a month instead of getting that extra Starbucks, I'm going to support this podcast I love. Don't make me send, well, we can't lean on Ira Glass, so don't make me send your friends to have me mock you. Please consider giving. It doesn't take a lot to make a huge difference. And we are grateful, and we try and make it worthwhile for all of you. We have Patreon office hours most Sundays. We have special rewards. You can get your name on our website. And most of all, you have my complete thanks by name. I will thank you as I read your names looking at our Patreon.
Patreon.
So let me thank you.
Patreon allows us to make this information 524 episodes of astronomy information available to anyone who wants to listen to it and learn about the universe. We don't have to put it behind a paywall. This is our way to make it available to as many people as possible, and we couldn't do this without the support of the patrons. So if this is a model that you support, if you like this, then definitely get involved. Go to patreon.com/astronomycast and pitch in. All right, thanks, Pamela. We'll see you next week.
Thank you, Fraser. See you later. And now we save.
Okay.
Boy. So this is episode 524, I'm gathering.
Yeah.
My dog just sighed the saddest sigh.
Oh, that dog could be out barking at a squirrel right now, and you won't let her.
Well, it's the non-barker who sighed the heavy sigh, because he would like to just be sitting outside.
Just give us 1 second, and then we will take your questions. Okay. I won't upload yet, but I'll put Dropbox open just so I remember to upload. Otherwise, Susie will be sad.
It is true. It is true.
Okay. Bill Sugden says, wow, Susie must be getting about $5 a month. I hope she gets more than that. Steve Chisel had a whole bunch of questions, so I want to go through some of them. Which adjective is correct for what is improving in our estimates? Accuracy or precision? Are we getting more accuracy or precision?
We are slowly improving both. Different techniques improve different things. So accuracy is how well you know the true number. Precision is what is the error bar on your on the measurement yourself. Itself, not yourself. So I have a ruler on my desk. I don't know why. And if I were to snap off and not notice I snapped off the first 4 millimeters on this, I could very precisely
be inaccurate
to a 32nd of an inch or a millimeter measure the size of something, but I wouldn't be accurate because I'm missing those 4 millimeters. Now, if I had a ruler that was only marked in like every 3rd millimeter and quarters of the inch, but it was complete, it would accurately measure the distance, but it wouldn't precisely measure the distance. So depending on how we measure things, we are getting both more precise and more accurate, but the two don't always get improved simultaneously. That's actually a really good question.
Yeah. And then Steve wanted to know, if a star's angular velocity at its equator differs from its poles, how does that variation influence the accuracy with which we can measure the star's age? So
it comes down to you have to watch things for a long time. They estimate they have a 15% error in using the gyrochronology, and that 15% does include the fact that these variations in velocity occur. Now, when we're looking instead at the Doppler, Doppler broadening of the lines due to the rotation of the star, the Doppler broadening takes into account the difference in velocity because you're still seeing those extreme velocities in the light coming from the star.
I mean, even knowing how quickly the sun rotates is kind of a complicated question. And we have that fairly well measured because the sun doesn't rotate at the same speed at different latitudes. Parts of it are swirling faster than other parts of it as it turns.
Yeah.
So
Yeah.
is it the magnetic field of the sun that's turning that you use to measure the speed? Is it the speed of the sunspots as they pass around the equator? Is it regions that are closer to the poles? So it's
And with objects like Saturn, we don't actually know how fast they're rotating.
yeah. Right. Well, I think they figured it out because they were able to see like the magnetic field interacting with the rings or something like that. So they were finally able to nail it down to a level of both accuracy and precision that they were happy to see. Snarky Bojum says, "I love the book reading recommendation, guys. More of those." So, what are you reading right now?
I am rereading Brandon Sanderson's Cosmere series. I am currently in the Mistborn series, and yeah, I am rereading books because I can't necessarily afford new ones right now. So yeah, it's a long enough series. A new book came out. I figured it would take me a while to reread all of them before I could read the new one.
That's cool. I am reading the. I get a bunch of books. I usually get my science fiction through like Humble Bundles. So they have like Humble Bundle ebook bundles.
Yeah,
and so
I get
you'll
those
get
as well.
like 20 books for $15. And now most of them they're all the beginnings of series, and so and my wife tends to read a lot more of them than I do, and so so she's got tons of she'll go like, I read this one, it was okay. This one was weird. There was like some kind of intelligent squid or something. So, and she has no context. She just like opens up her Kindle and there's the next book, and so she reads it. And then of course I get sent a pile of books all the time, so I'm trying to get through the books mostly so that I can be prepared for when I do an interview. I mentioned last week I'm reading the Three Body Problem series. I'm now finished the second book. I'm into the third book. The third book is great. A lot of people really loved it. I really like it. It has one just catastrophic problem with it.
Yeah.
It sort of has this really bad sort of misogynistic tone, which is really, I think it didn't have to be there, and it could even be like the way it was translated and the way the translator approached it. But I can imagine other ways they could have sort of gotten to the same conclusion without having to go that path. So it's still a really compelling book, really great ideas, and there are sort of twists and turns in it that you're just like blown away, and I really enjoy it. So
something else that I've been up to is on my personal Twitch channel, twitch.tv/starstrider. I've been in the evenings, not all evenings, it's been inconsistent lately because I scratched my cornea. Don't do that.
Yeah, that makes it hard to read.
I've been reading through books that are out of copyright that are on Gutenberg,
That's cool.
on Project Gutenberg. And right now we're reading through From the Earth to the Moon. And the science in this is so spectacularly bad.
Oh, no.
But it's so bad, it's glorious.
Yeah.
So I am going to at some point release all of these as an audio series with accompanied annotated, here is why the science is wrong, and use it as a teachable moment of gloriously bad science.
It's pretty great that finally copyright has updated another year. We've been like 20 years that nothing has come out of copyright, and finally things have entered the public domain, and we can actually
any author that died in 1948 or earlier is now fair game.
I don't think that's true.
Yeah, it's based on when did the author die.
But I thought it was when the thing was created.
No, it's when the author died, because copyright is, so there's exceptions with magazines, but novels, the copyright belongs to the author up until I guess it would be 70 years after their death.
Yeah. But the point is, there's lots of places where you can go and find what are all the new stuff that have come into copyright free, public domain. What are some books you can read, and so you could stay pretty busy. And some old books are just great. So,
And it's a bit morbid to be doing the what authors died in 1948,
yeah.
but that is what I have been doing, and I have not regretted it.
The other
Mostly.
thing that I love to do is I use my local library quite heavily. And so I just any book that sounds like I want to read it, I will just go to my website, go to their website. I will put on a hold onto the library, and then within the next couple of weeks, the book will come up for they'll my hold will come through. I'll just go pick it up and read it and then drop it back off and move on. And
Yeah.
sometimes I things sort of line up and I get 5 or 6 things all at the same time, and then I have to I can only read 3 of them. And so what I'll do is I'll just toss them back and then put another hold on them, and then another 2, 3, 4 weeks later, I just go back to the back of the line again, and then I just wait for my turn again. So but I've put a real emphasis on reading again. I'm really trying to minimize, at this point now, I don't really spend any time on social media. I really try to minimize the amount of YouTube videos that I watch, although I'll watch them when I'm riding the bike. But apart from that, I don't really do that.
I hope, ride a stationary bike.
Yes.
Okay.
Yeah. And then, podcasts. I love to still listen to podcasts while I walk or do yard work and chores and things like that. And then I've really forced myself, I plug my computer and my phone in other rooms, and it's only books to bed. And it's been great. I've been, it's pretty funny because you could feel the craving. You're like, oh, I really want to get up and see what the response to that tweet that I made on Twitter is. And then you're like, nope, all I got is this book I'm reading. So.
And I am addicted to audiobooks, which are harder to get at your local library unless you have a CD player, which I do not have. But with audiobooks, I'll get into an interesting part of a book and be like, okay, my house is going to get really clean so that I can just focus on this book.
Yeah.
And that's my happy space.
You can, with my library, there's a thing called Overdrive. And so you can take out audiobooks through this system. Ooh. But it's super weird, right? Because it's not like it's a physical copy of a book that you can you actually have to pick up. It's just like some kind of digital rights management to try and keep it all organized, which is kind of ridiculous. I wish there was a Netflix of audiobooks. I mean, Audible obviously is the Netflix of audiobooks, but it's not the same, right?
No.
Audible costs
There's limited titles on the Kindle Unlimited.
Yeah, well, I don't think there's any. Are there?
No, yeah, there's an audio
okay.
Kindle Unlimited has audiobooks, but it is a limited suite.
Right.
So what I found is I'm actually better off. Up until December, I'd been doing 2 books a month, and that wasn't enough books.
And it's just too expensive.
Yeah.
Yeah. So it feels, I feel like the demand for this does not match the supply. And I think that, if there was a $10 a month all you can eat or $15 a month all you can eat audiobooks, I think that would be a lot more successful than the way Audible works today. It's kind of ridiculous. It's too bad.
The problem that goes into it is there's a much higher production cost in making an audiobook as compared to a paper book.
Compared to a movies or a television series that you see on Netflix?
Yeah.
No.
Well, so you have to hire someone who wasn't already involved to do the narration, and then you have to hire someone who wasn't already involved to do the production. And
I think there's a huge opportunity for someone, even Netflix, to buy the audio rights to audiobooks and then just read them out. And people are trying to make the Netflix of podcasting, right? And I mentioned this, why doesn't
Spotify?
You know who could do that? Netflix could be the Netflix of podcasting. All they have to do is just add podcasts. I mean, if they're going to spend $100 million on Friends or or they're going to spend whatever, several $1,000,000 per episode for a television series that isn't very good. Can you imagine if they were willing to spend, say, I don't know, pay for the audio rights of a book, $10,000, and then another, say, $5,000 for someone to read the book, and then they would have an audiobook that
I
you could
wish
listen
that's how
to.
much they paid someone to read a book.
Yeah, I know, right?
Yeah.
So the point being that it's a ludicrous amount of money for you to sit down and read the book as talent, and yet they could start adding a ton of books to Netflix, to your existing Netflix account. So
Yeah.
I think that right now there's a gigantic market opportunity for audiobooks because podcasts are free, which is kind of wrong.
Yeah.
Right? It's weird that all while television has entered the Netflix era, and people understand that sometimes it makes sense to pay for television that you really like that has high production values. There is no market for, apart from advertising, which sucks. So
Yeah.
I think that there is an opportunity. I think Netflix is the right machine to do it. How hard would it be for them to just add audio to what they already do?
Yeah, and they have the algorithms.
Yeah, it's amazing to me that they don't do it. So if someone wants to start a competing series, buy the audio rights to some books, read them out. Boom. All right. Any more questions? We've got about 4 more minutes, although clearly we just went on a big rant. So there you go.
We did that last week.
I know.
Too.
Thanks, Snarky Boojum. That was a lot of fun. So yes, we like to talk about books that we're reading.
And I have completed narration of my first audiobook that I did commercially. I need to redo one of the chapters because it had an accent for a foreign country in it that the first time I did it, wow, it was bad. So I need to redo one of the chapters. But yeah, I know exactly how much they pay for audio.
Steve Chisel is saying those costs should be accounted for in the normal publishing cost of literature. So should the cost to publish in Braille. I think that's a great point.
Yeah. And unfortunately, neither are, which is why nonprofits do both in many instances.
Yep. Snarky Bojum saying, when's the next live observing session? I don't know. The weather in California has been rotten. Just awful. Every time I've tried to open up the telescope, it's been pouring rain. It would just fill up with, David Sims just popped in and said hi. Hi, David. Thanks for the recommendation on Kalpana 1, which we talked about at the Weekly Space Hangout. I'm super obsessed with this now, and I want to do an episode on it. So thanks and you and Larry Beckham put me on down this rabbit hole. So I just want to thank you for wild entertainment of a really cool idea for a rotating space station that's stable. So the problem with an O'Neill cylinder, right? The big gigantic O'Neill cylinder is it rotates like lengthwise and the thing turns, right? And you live on the inside with your artificial gravity. But the problem is that an object like that isn't actually stable in its rotation. Objects like that,
precesses.
Yeah. So the problem is they want to be stable over whatever is the larger, the length, the more. And so what an O'Neill cylinder really wants to do is rotate end over end.
Yeah.
And so you have to force it through mass redistribution or thrusters or something like that to have it spin in the way that makes it a proper O'Neill cylinder. While say a Stanford torus is more like a ring and is more stable, but then you don't have a lot of living space because it's like this. It's like a donut that you're trying to live on with curved sides.
Yeah.
And so this idea of a Kalpana station is sort of the best of both worlds. It's cylindrical in shape, but it is flattened, and so you can be inside of it and live on the flat area, but have it be stable. And I love that it's named after Kalpana Chawla, who was the one of the astronauts who died in the Space Shuttle Columbia disaster. So anyway, I'm going to do a deep dive on these stations at some point. It's such a great idea. And we've reached the end of our hour.
We have. We have.
That's it. So,
Okay.
thanks everyone for watching, and thanks, of course, to the mods and to if you want to join, we've got like 2 days or 3 days until Google Plus shuts down, destroying the communities forever. So, if you want a place to go and hang out with some good friends, come join the weekly Space Hangout crew. Go to wshcrew.space. They will hook you up. They'll give you access to the chat that shows up in our shows. And yeah, good times. All right. Thanks, everybody. I'm going to go pick up a kid from a ferry.
In- Enjoy.
Remember, I live on an island.
No, I know. I still imagine Tinkerbell, though.
I know. That's when not on my island. That's not when you say the word ferry.
I understand.
Operate our lives around all these ferries. All right.
But wouldn't it be so much more cool if you had Tinkerbell flying back and forth across the harbor instead?
No question.
Okay.
All right. We'll see you later.